The state-of-the-art Ed Lumley Center for Engineering Innovation is the new home to the University of Windsor's renowned Faculty of Engineering. A faculty that offers a wide variety of opportunities that prepare students to creatively solve the practical problems that face our society. With degree programs ranging from aerospace and environmental to civil and mechanical, from automotive and industrial to electrical and material, becoming an engineer has never been more exciting. There's also co-op opportunities that allow students to earn money and gain valuable real-world experience, all while completing their degree. The facility itself rivals the technical sophistication of any post-secondary institution in Canada and was constructed to meet the highest environmental standards and to provide learning opportunities throughout. Aside from world-class labs and classrooms, the Center for Engineering Innovation features a green roof, water recycling, low-energy heating, and other sustainability systems. This unique combination of our state-of-the-art facility, Windsor's unique climate of cooperation between academic, business, and industry sectors, and some of the best minds in engineering ensure that our graduates' career opportunities are outstanding.
Hey, good afternoon, everyone. I'm Rob Whent. I'm an industrial technology advisor for the NRC-IRAP program here in Windsor-Essex. I'd like to welcome you all to today's breakout session on aerospace. And just a reminder, we're going to have 3 presenters today, and I'll introduce them in a moment. Just remember to post any questions for them individually in the Q&A session box on the screen. And we'll have a short Q&A after each presenter is finished. As I mentioned, we have 3 panelists for today's session. First up is Nick Dimitrov, the Senior Vice President at AIS Technology Group. And Nick oversees corporate strategy, operational excellence, and external relationships with investors, strategic partners, and customers, along with executing corporate strategic initiatives. Nick's got over 28 years of automation industry experience with an extremely strong comprehension of engineering, software development, and machine vision. So over to you, Nick.
Thank you, Rob. I'll share the screen. Thank you for the opportunity to present our latest product, which is multi-format vision system. 1 second. This is a very brief history of our company, and I'm saying some of these developments that we're going to show you here date back in our Radix Inc. Days. Sometimes it is obviously a lot of effort, development in the market to be right to deploy new products. We started in 1994 and progressed strongly throughout the years and developed a few products starting around 2006 to date. Our driving factor when we get out of bed and go to work is automation. We have excelled in developing many vision based products. Lately, we have focused on artificial intelligence and marrying the artificial intelligence vision systems together with machine vision algorithms. There are significant challenges as the deploying vision systems, as the computers are increasing in power, the cost of the cameras are going down. Many of the traditional vision inspections are fairly easy, but as always, the industry is pushing the limits. So in many instances where vision was applied traditionally is shifting towards some more challenging areas where typical vision systems does not have the luxury to have the traditional line of sight. The complexity of the products are also increasing, and obviously the cost of everything, as everybody's aware, is going high. So our MVS or multi-format vision system is addressing some of these challenges. We created a matrix that kind of shows if MVS or multi-format vision system is a product that may address some of your challenges. For example, if the repeatability of the part position is poor and the part is not presented in the same space all the time, multi-format vision system would be a candidate. If the line of sight is also not there. If the inspection has to happen, for example, inside a confined area or inside the vehicle, typically you cannot put a fixed camera, and sometimes robotic applications obviously add additional safety concerns. Additionally, in aerospace, for example, even though every part is traceable with the serial number, sometimes it's hard to employ machine vision to read data metrics because the parts are marked with human readable. So this is where artificial intelligence also excels in reading human readable characters. Another very important aspect of inspection is if the number of inspections are growing exponentially based on the part complexity. This is where NVS would also be a candidate. So these metrics could be applied in your specific area and see if this works. But what is NVS? NVS is a multi-format vision system. It's a mobile application, part server-based application. What we have done with this product, we are allowing different camera technologies to be used to generate an image, and that is sent to a server where artificial intelligence and traditional machine vision algorithms are being used to analyze the image and report back the status of the inspection to the mobile user. Obviously, the mobile phones are integrating cameras with high resolution and good characteristics, and today we can say that they could be used for inspection of assembly operations and so forth. In our particular solution, I'm saying we are not really stuck to cell phones only. They could be fixed mount cameras, they could be mobile like Android or iOS device. The camera could be mounted also on a robot. Everything everything that can generate an image is basically sent to the server for analysis, and further on the results are sent back to the user. This slide shows in a nutshell the architecture. It does show that the image acquisition is generated by the mobile device. It's sent to the server side for processing and obviously storing of all the images together with additional data, for example, the user who did the inspection, the serial number of the entity that we're inspecting, and so forth. Obviously, as it is mobile, it has to run either on your Wi-Fi or on the cellular network, going to the server, which can be on premise or eventually on the cloud. Again, the NVS or the multi-format vision system runs in two particular modes. The first mode, it's a PLC mode where the process requests when the image has to be taken. So the PLC, or the programmable logic controller, determines the time when the inspector has to take an image and sends a message to one or multiple mobile devices indicating that an inspection has to be taken. Once the image is taken, the image is transferred to the server, the processing happens. It is either a pass or fail result. That result is sent to the operator to indicate if the inspection was successful, but also sent to the PLC for further processing and verification of the processes. The other mode in which this application can run, it's an audit mode where the PLC is not really involved. This is typically in repair base or where manual audit is taking place. So the operator would logging into the application, it will select the entity that needs to be inspected, obviously enter or read the serial number from the entity, perform multiple inspections as required, and those inspections are, together with the images and the status, are obviously stored on the server. So typically this is really useful when the assembly goes through different levels of assembly process, and where level 1 cannot happen, has to happen before level 2 happens. The back end of the application is server based. There's a full SQL Server database. Reports can be generated to indicate if the certain assembly has passed all the inspection points and so forth. This is kind of giving you the user interface. When the operator loads the app on either iOS or Android device, they will read the serial number from the device. There's a little camera app that reads the serial number. They obviously can put their user ID. In many traceability systems, it's important to know the ID of the inspector. Once they log in, they're presented with number of inspections that have been assigned to that user. So certain inspectors can do only certain inspections. Once they pick the inspection, they actually collect the image and send it over to the server. What type of inspection can the system do? Certainly assembly verification. It will let you know if certain components are present or absent. It can detect flaws in the surface. If the surface has scratches or some elements, let's say of the welding pattern are not there, the vision system will also report that. And as I mentioned before, reading OCR or human readable characters, it's a very strong feature. It's not only reading the characters, but also applying like a regular expressions or a grammar where certain characters have to appear in a certain position. We can discuss now some potential applications, that can take place. Certainly, the MVS can be used for troubleshooting of repairs. If the entity, let's say that is maybe a 3D printer or some more complicated entity doesn't work, and we have to guide the operator to understand what is not working. This application can do a quick checks and let you know if the device is in a good state to perform the operation. In the automotive sector, it could be used for verification on the engine compartment if all the components are placed in the right locations. In this particular case, we're looking for presence of hoses, clips, the oil cap, and so forth. One of the applications that currently we're investigating, it's a pre-flight inspection check where the inspector of the airplane walks around the airplane, takes pictures of the regular pre-flight check, and gets the help from AI to make sure that everything is good. The good thing about this inspection is that every inspection will have an image and stored in the database, which will be an additional verification feature that the pre-flight check was performed by the inspector. Again, going back to the OCR inspection, which is this is an example from an aerospace customer. Many parts are marked with unique serial numbers, and they undergo several surface finishes, and the quality of the OCR obviously degrades as different surface finishes are placed on the part. So in this particular application, using an AI and NVS, we were able to read the serial numbers and verify the regular expressions, making sure that the serial numbers were formed correctly. So this is basically in a nutshell our NVS product. I'm open for any questions that you may have.
Thanks, Nick.
Thank you, Rob.
I couldn't find my unmute button, so I'm back. Pretty fascinating, and I was wondering if you could give us some idea of what it's like working for aerospace as opposed to automotive manufacturing that you've probably had your most experience with. Is there much difference in dealing with aerospace companies as opposed to traditional manufacturers, automakers, etc.?
Yeah, yes, Rob, for sure. We do have experience working with several aerospace customers. The challenges are, I would say, the same. Automotive industry has taught us well to perform within the very short cycle times. In aerospace, the cycle times are much larger, but there's lots of balances and balances and checks before certain technologies are implemented for the right reasons. So typically, the projects take a longer time than automotive projects, but they're equally rewarding once everything works.
And what type of cyber intrusion protection do you have in your systems? We know cyber has really increased in the past, 2 years. Is that built in as a fundamental piece of the platform?
So I have to say that we run on the customer network, so all the cybersecurity elements have to be implemented on their Wi-Fi network, or like I said, the cellular network. There are limitations in the software that we can limit to what network they can connect to. Currently, we're also working on a feature where they can connect. The user can connect using a Bluetooth, which we are completely avoiding the internet connection. It will still go from Bluetooth to wired. This is a feature that was requested by some customers to avoid the Wi-Fi connections.
Sure. So when you're talking about mobile devices, you're really talking about a mobile device using a Wi-Fi network within a set parameter. They're not necessarily sending data via their data plan through Bell or Rogers, correct?
Yes, that is correct. This application is limited to the Wi-Fi within premises. It could be using the cellular network. I have this application loaded on my cell phone, and I'm using it as I go and show it to our customers. But in a typical application, it will be a Wi-Fi network that is deployed and managed by the customer.
So does aerospace have any specific requirements for cybersecurity based on the advancement in technology that they're working on? Or do you find that's really not much of a consideration when they're dealing with you? Because as you mentioned, they're dealing with that internally. Have you seen much increase in cyber preparedness?
No, based on our previous experience, obviously dealing with aerospace, you have to be control goods certified and employ certain procedures to ensure that during the development phase, the proper NDAs and sharing information is tightly controlled, and only certain individuals can work on that one. When it comes to deploying the solution, we work with the IT teams from the customer side to ensure that our application adheres to their procedures and standards. So each customer has their own procedures, and we have to work closely with their IT department.
Okay, fantastic. Well, thanks, Nick. Great presentation. I encourage everybody to continue to put questions in the Q&A box. We're going to go to our next presenter now, Andrew Good. He's a technology manager with the Jesse Garant Metrology Center. He has 10 years of working in the non-destructive testing industry, and he specializes in the industrial computed tomography field and X-ray technologies. Andrew, over to you.
Thank you very much. Yeah, let me move this out of the way here. So basically what I'm going to do is I'm going to give you a kind of a brief overview of what is computed tomography, because more often than not, we have a lot of people ask us, what is computed tomography? And computed tomography is basically an X-ray based technology. So there's basically four main components of computed tomography, and it basically has, you have a cabinet, an X-ray source, a table, and a detector. Now you put all these together, and the main components of that computed tomography system is your detection. So you have two major connectors in your computed tomography machine. Give me a second here. I need a little bit more volume here. So when performing computed tomography scans, you have linear detectors and digital detector arrays. Linear detector arrays are basically lines of pixels that detect and pick up X-rays, okay, and then that is translated into an image. Or you have a digital detector array, which is basically multiple lines of pixels that are then captured as like a full flat panel that then can be reconstructed into images. So what ends up happening is when you put them all together, you take several thousand projections during a 360-degree rotation. During that time, what ends up happening is these projections are attenuated, so they're basically converted to a black and white image, and then in the reconstructor, using a mathematical algorithm, you're creating a three-dimensional data set called a voxel. And what a voxel is basically a three-dimensional pixel with density information. Get asked all the time, well, that's great, what does that do? Well, First and foremost, what everybody is usually very familiar with any based X-ray technology is voids or inclusions. So basically what ends up happening with computer tomography, however, it gets a little bit deeper. So not only can you detect voids, cracks, and inclusions, you can actually quantify them. So basically you can quantify them as a method of diameter, volume, direction, compacticity, sphericity. Okay. However, you can take that one step further and you can actually overlay a CAD file that contains machining information. So that way, areas where it's critical to machine, you can actually see if you're drilling into porosity. So basically helping you remove any scrap castings. The next one is you got wall thickness. Wall thickness is a very interesting one because it's very similar to using like a Magnum mic or any sort of ultrasound. However, not only does it just do the outside or where you can reach, it'll do throughout the entire part in all areas, in all locations. So basically you can calculate the wall thickness and set tolerances based on that wall thickness in different locations. Now, there's another really neat thing that you can do with wall thickness analysis that I didn't show here, is you can actually measure the air inside the cavity. So you can actually find the cubic volume of basically a core or a bore to show how much actual wall or air wall is in that particular area. But when we start getting into something a little bit more complicated with computer tomography is we need something called surface detection. So that's great that you can see these voids or you can kind of measure the wall thickness. However, if we're going to do anything more advanced, we basically need to surface it. So what ends up happening is we use something called an isosurface or an advanced isosurface. So basically what it does is it more or less takes where it knows air is and material and basically creates a local adaptive line around the entire area. Okay. Now you got to remember this is in full 3 dimensionals. Now this can actually be accurate to 1/10 of a voxel. So you can actually get very, very high precision on this, which then helps us to do measurements. Because measurements are basically, what is CT, the new style of CT, okay? So what you can do is using a CAD file or a part print, you can actually develop an entire measurement plan very similar to what you can do on a CMM or any sort of structured light or camera-based system. However, the major difference is obviously since it's an X-ray based technology, you can actually measure the entire part throughout without cutting the part, okay? And not only does it conform to your QDAS, it also has AS9102 Form 3, okay? It'll actually do full complex GD&T callouts, both MMC, LMC, your compacticity, sphericity, all that is included in there. And then basically what ends up happening is once this measurement's been created, so in this particular case, 1,400 individual measurements or 3,912 geometry elements, to apply that many after scan time is 45 minutes. So from when you put the part into the machine to when you actually get a report spit out, it's 45 minutes, which traditionally you wouldn't be able to do. Now, the big thing is there's always, yeah, that's great. There's a measurement. How do you prove it? So the beautiful thing with CT is because it's all digital, you can solve this and provide traceable proof by using what's called IQIs, or you can use reference objects. So in this particular case, what we're using is bar ball spheres, okay? Because bar ball spheres, a sphere's center is independent from the surface threshold value, which is very important because that removes any possible sources of error in the imaging chain. So basically a known distance between the center of points between two spheres can be measured, adjusted, and can also be verified using traditional means. Now, with the ability to also import textures from a different inspection method, i.e. structured light, you can actually capture scribe lines. So that way when you're doing point-to-point style measurements, or you're trying to do correlation between a traditional method and computed tomography, you can actually take it apples to apples. You can actually take it in the exact location where the CMM or hand tool took it. Now, CADs are a very important part of using CT because there's lots of different types of analysis that you can perform with CADs. The most common is obviously your actual nominal comparison, which basically spits out a nice little color chart showing you where does the actual part deviate from the CAD file. Now, you can use this information to tolerate it. So if there's areas of additional wall stock or positions or bores are out of position, this will automatically flag it and spit out a nice little report and picture. However, with the advent of especially being driven by the aerospace industry is PMI importing. So basically part measurement information is being heavily pushed. So what ends up happening is the part PMI information contains all measurement information from the time of design. So that way, when it gets imported onto the actual data set, there's no user interpretation of where the measurements should be taken because those were preset from the actual designer's intent. But what happens if you don't have a CAD? Well, here's the beauty. Using CT, you can actually overlay or create what's called a golden surface. So you can take multiple of the same part, say legacy parts, and you want to make a CAD, you can actually overlay them and create basically a mean, max, or an average CAD file from those scanned parts. Okay. Now, yeah, that seems interesting. Yeah, okay, you could do it probably on a, with a designer and some time and some tools. However, where this actually really becomes important is when it comes to automation, especially for certain tools that are old or are starting to wear, or you just don't have the CAD for. So what ends up happening is all this information can be assembled into what's called an evaluation. So what you can do is when you put in that part, it'll take every analysis that I just illustrated and will compile them all and spit out either something as simple as a green or red, or it'll provide you with detailed reports for each individual analysis. So you can actually quantify an actual aerospace casting to their specifications in less than 10 minutes. We've even done it down to less than 4.5 minutes because it's fully expandable. You can add as many workers as you would like, which helps with computational power and acquisition time. Okay. Do we have any questions?
I don't see any in our Q&A box, but thank you, Andrew. Great presentation. If we do get any questions, we will pass them along to you, and you are right on time. So thank you very much for that very enlightening presentation.
Thank you very much. Appreciate it.
Okay, and stay tuned at the end. We'll open it up for questions after our next presenter. And next up is Dr. Mohammed Belassel. He's a research and development manager at Proto Manufacturing. Mohammed has 30 years of experience in the field of X-rays and over 25 years at Proto. He's co-authored books and presented and published over 50 scientific papers and in the field of X-ray diffraction at international conferences and journals. And he holds 5 patents in the field of X-ray diffraction. Mohammed, over to you.
Okay, thank you, Rob, and thank you for the introduction. Thank you, everyone, for organizing this conference. I will share my presentation. Can you guys see it?
Not yet.
No. Okay, let me go back. I thought I did. Okay, share. Okay, let me do it again.
Okay. There we go. Now just go full screen.
Okay. All right.
Perfect.
Okay, very good. Thank you. My topic today is about measurement of turbine blade single crystal orientation using robotic low X-ray diffraction technique. This is aerospace application. The project is funded by NRC-IRAP, and we thank you for that. And in particular, Vladimir Franju, who actually selected this project among others. And it's a great topic, and I will share my findings on what we do at Proto in this field. The work is related to turbine blades used in jet engines, and these blades are used in the hot section of the engine, where the temperature can reach about 1700 C. The material used for the turbine blades is nickel-based materials, and it can melt actually at about 12 to 1300 C. Of course, with all the cooling technologies they have, these companies, they can lower the temperature in a way it goes below the melting point. And of course, they have also ceramic barrier coatings on top to help reduce the temperature. With efficiency now that's going up and up and up, the temperature of the engine is going up too. That means they have to avoid catastrophic failures because of these blades that were made of polycrystalline materials in the past. They have to go to single crystal materials. One of the problems they have with the presence of the grain boundaries in materials is creep rupture, and also associated with that oxidation, slippage, micro cracks, thus reducing the life of the blades. When they started back then, they tried to eliminate the grain boundary along, like it's perpendicular to the grain longitudinal direction, in the radial direction, or where is the centrifugal force is applied. And then they created these, which you call direction solidified turbine blades. And later on, they went with single crystal turbine blade altogether. These are pictures of the blades. This is an equiaxed structure. We have many grain boundaries. And these are, and the second one is the directionally solidified blades, where we see the grain boundaries along the blade, not perpendicular to where is the load. That means this helps, but not enough. And going to a better structure now, they went with single crystal, where we have one grain for the whole entire blade. Although they manufacture these blades to be single crystal, sometimes they may get what they call strain grains that can grow from the bottom or inside in the middle. It depends on a lot of physics like thermodynamics, and these can be problematic. But of course, some of them can be, if they exist, can be thrown out, and some of them may be accepted depending on the misorientation of that grade. They have all kind of criteria to accept it, to reject it. How they make these blades? They make them in ceramic molds, either use single crystal seeds to start the solidification, or they use sometimes just chilled plate with columnar grain structure block. That means it has many grains, and thanks to this kind of corkscrew shaped geometry, they can select only one grain coming out and the rest don't come out. And from that, they can grow the grain in the mold. The direction of the grain itself is 001 by default, and this is what they want. And why they want that? It's because if you look at the structure of the material, which is cubic structure, and you look at the 100 direction and 110 and 111 direction, they looked at the fatigue of these materials or blades, or could be samples oriented in these directions, and they found that the 100, or you can say 001 is the same thing, has actually better fatigue resistance. That means with this direction, they can afford actually better efficiency and long life for the engines. How they do now to verify the direction of these blades? We use X-ray diffraction. In contrast with polycrystalline materials, we can get the bearing coming from multiple grains oriented randomly in the material. Here we see only one grain, and we see spots, and each spot corresponds to an HKL plane in the material. And it depends now on the orientation of, let's say, the crystal. These spots will move with it. This is an illustration of the images we can get from these materials. This is in back reflection. We'll see the spots, how they are lined in kind of hyperbola shapes, and which we call actually in diffraction the zone axis. Or if we go in transmission, sometimes if we need to go through the blade, then we see circles. And these all the spots corresponding to planes or crystallic planes in the material, which we call also HKL. The angles measured with this technique are many, at least 3 basic ones, which are gamma, delta, and kappa, within 3 main axes. And also we have other ones called theta, kappa, alpha, and rho, depending if you're using UK or US conventions. And all these angles are important for the manufacturers to know how the blade is behaving when it's inside the engine. And also to make sure that the orientation, which is here, like the theta angle, is oriented within a certain degree from 0. And usually it's, for all manufacturers, maximum is 15 degrees. It's 15 degrees above, the blade is rejected. Now, the instrument we use for these measurements, this is a Lowy instrument, we call Lowy instrument, where we can place the blade inside on the platform, and close the door, and we start the measurement on the blade. This is a typical image we get, and here we show in green the overlay on top of the spots. This overlay is calculated, is all theoretical, and we match this manually. There we can do it automatically in some cases, but it depends on the image quality. Sometimes it's hard to do. And in this case, actually, we are calling to use maybe some machine learning to improve the process. The problems now with using these equipment at this point, I mean, we came a long way from the beginning when they started back then in the 70s. The process is open enclosure door. From the tray, remove the turbine blade and type serial number by hand. Place the turbine blade in the fixture inside the enclosure, close door, launch a measurement from software, then image acquired, match the spots with calculated overlay manually. And then we see the result displayed instantly. And then depending on the criteria used for this type of blade, it could be accepted or rejected. That means that the user will take the blade and put it himself in the rejected bin or in the accepted, back in the accepted one. This is very repetitive and time consuming and prone actually to shoulder injury. When you place these blades inside the instrument, you know, you can go like hundreds a day. It's really rough on the muscles. That means we need to kind of try to improve on that. Other things also, mistakes can happen. You type numbers, or you do the overlay, maybe you not match it correctly. Yeah, you may get bad results. All this said, the current production facilities cast hundreds of turbine blades. So actually every engine can take at least 200, maybe sometimes more. It depends on the engine. And also they grow what we call seeds to grow these blades from the seeds, and this is also have to be verified for the orientation. And then the single crystal blades now is constantly increasing with the number of engine built, and also replacing all the old polycrystal blades. Hundreds of single crystal turbine blades per engine are measured every day, and I know some factories they get thousands. Manual placing the turbine blade is time consuming. It takes at least a minute, sometimes even more, and depends on the complexity of the blade. It depends how you put it, how many things. Manual instruments are costly and reach the limit at this point, and actually limit productivity. Human errors also exist and is required to be eliminated. The solution is to use robotic Lowy instrument. In this case, instead of having the operator outside here reaching with his hand to place the part and then close the door, measure the orientation of the blade, we place a robot, a 6-axis robot inside the enclosure. And here we have an OCR, actually who can read, a camera can read the serial number automatically. And then the robot itself picks the part, read the serial number, place it in front of the X-rays. Here is the X-ray tube and this is the detector. Perform the measurement, do the calculation, accept, reject, and then the robot automatically will put it back in the tray or put it in the reject bit. What we have so far at this point, we actually just finished the layout of the design, but we have the robot placed inside the enclosure. This is from the REACH study, simulation study we did lately. And here is the tube, the detector, the robot, the bin, the reject bin, and the tray. And actually here is the OCR placed here. And this is the actual system with enclosure and the robot already mounted inside the enclosure. This is ongoing. The project actually started in June 21, and it's going until June 22. That's the IRAP funding duration.
That's fantastic. Mohammed, I just wanted to give you an update. We are going to go to the main stage in another minute, so if you could wrap up, that's
quick.
Perfect.
Yeah, that's conclusions.
Great. Thank you.
Conclusion: single structure is the solution to enhance fatigue life of jet engines. The demand for higher efficiency of jet engines, the industry is trending to replace more jet engine components with single crystal structures. This is already extended to vanes, not only the blades themselves, other parts in the engine. The vintage Lowy inspection method, manual handling of components, is not efficient nor productive. With the increase of the number of single crystal components, the solution forward is to introduce automation. The industry has already implemented automation for other processes and now looking into automated Lowy inspection. This will contribute to higher productivity, better consistency, mitigate human errors, and avoid shoulder injury. Thank you for listening to my talk. If you guys have any questions, you can reach me at Proto Manufacturing anytime. You can come visit anytime, and thank you.
Perfect timing. Thank you very much, Mohammed, for another great presentation. And I'd like to thank all of our presenters today for some great information. Unfortunately, we won't have much time or any time to take any further questions. But again, I'd like to thank everybody for coming today. Mohammed, thanks for the shout out to IRAP. I was involved in this project as well, so it's pretty cool. All right, everybody. Thank you. And we'll be heading over to the main stage for our keynote speaker. Thanks, everybody. Have a great one. Yeah.
Thank you, Rob.